Right, good noon everyone. Let's start from the last class again. Okay, now when we covered this loss function, I did not tell you that this is a loss function for V1. This is not the loss function for V2. There's slight differences. I will cover those differences now. Okay. Now, first of all, when we train the model, this is not there, this is not there, and this is not there. Right? We first start with this particular guy. Now, in 13 cross 13, each block has how many templates? 5, and one block can have 5 objects, which means I must check 5 times here, which we're not doing here, right? So this is going to be slightly different. How is this going to look like? I will have one more submission here, which is j equal to 0 to b. This guy is going to come here, right? And this one object is not going to be one object I, but one object ij, and this pi is not going to be pi but pij. This part clear?
So j is from 0 to 5.
J is from 0 to 4 or 1 to 5. Right? The first modification which is required for this particular loss function, because now I have to check for one box, 5 templates, every single template I have to check it for. Second thing which is going to change is that all of these are Cijs. That's all. Everything else remains same. So in YOLO V1, what was happening is one box can predict only one class. One box can only predict one class. It must use the available templates, and there were 2 templates per class, per box, either a horizontal or a vertical one. Now what we have done, we are forcing it to look at every single template, and each block can predict up to 5 objects, which means I have to have pi and pj. Is this part clear? Any question on this? Right, so alternately I can actually take this out, right, and just use this in front of everyone, lambda coordinate being there wherever they need to be. Cool. Okay, now second thing, if you look at YOLO V1, this is what YOLO V1 is doing. In YOLO V1, we are going to start with 448. Then we have this dark net architecture, which gives us 7 x 7 x 1024. This is our VGG network. We collapse it to 4096 fully connected layer. We reorganize that layer into 7 x 7 x 30, right? And then this is connected to these many objects. Now, how many bonding boxes we have? We have 2 bonding boxes in YOLO V1. And how many classes we have? We have 20 classes.
What's the benefit?
Sorry?
What's the benefit of transforming first into fully connected and then like rearranging it?
What is what?
What's the benefit for the last 2 layers to be there in a way they are?
Here?
Yeah,
It's an architectural decision they are taking. This is VGG. So they are using a pre-trained model. You can't directly convert this into 7 x 30. If you do that, then you have to train this layer also. So we don't want to train this layer. Because we don't want to train this layer, we have to add our own layer which we are going to train. Right? Because every object detector uses transfer learning. So you're not going to be training these guys. These are the fixed layers. They train the darknet from scratch like VGG for the objects they are interested in. But once training is done, you don't want to touch this layer. These are the green guys are the guys which you're going to be training. Right? So if we have, is this part clear now?
But there is 5 bonding boxes.
Sorry?
You said 2 bonding boxes. So 5G plus 3.
You pick 5 bond. This image I have taken is showing 5. You pick any number of bonding boxes you want. This image is showing 5. Is this clear? Any question here? 25 classes.
Why we need 2 fully connected?
Sorry?
Why 2 fully connected?
There's only one fully connected layer. This is 7 x 7 x 30.
That's on the reshaping that's happening.
Just to reshape, you have to get something like that. And fully connected layers are very good in transferring the reorganized information. They're not really good in transferring 2D information. Now here we don't need 2D information. The structure happens to be 2D, but you don't want 2D information to be there. Every single block is supposed to carry 1D information, right? And one block is not dependent on the block next to it, which means you're not carrying 2D information, Is this part clear? This is not carrying 2D information. The structure happens to be 3D, but it is carrying 1D information. It is carrying it is carrying two bonding boxes, and in each bonding box is carrying X, Y, Z plus the coordinates. This is not a 2D information, this is 1D information. So the structure happens to be 3D, but it's carrying 1D information. Right? So that is why this structure is fine. This is YOLO V1. Now V2 is slightly different. In V2, what we are going to do, we are going to start with our normal VGG architecture, and in that VGG architecture we are again starting at 416. You see, we are not starting at 448, we are starting at 416. You start at 416, you convolve, and finally you are at 26, 26, 512, right? You see 26 is a multiple of 13, that is why we are at 26. So they have smartly reduced it to 26. Now when you are at 26, why the reason this is shown as 26, because you remember that we have a skip connection. That skip connection happens from a 26 cross 26 layer, but finally we need to concatenate it with, this is how your network architecture looks like. Initially we have these convolution layers. After the convolution layer we are going to create this skip connection. Now this skip connection is coming from a layer of 26 cross 26. You can read that, right? 512 26 26. Now that I have to concatenate here. So I have to add this reorganized layer. And what does this reorganization layer look like? What is the full form of STD? Space to depth, right? There's only one definition of STD. So what you're going to do, you're going to take your 26 cross 26 and convert this into 13 cross 13 cross 4, right? That is what we do for our skip connection, unconcatenate, and these two layers we are adding. Now here, if you see what we are going to do, once this part is done, I have my conf 13, 5 and 12 will be 2048 13 cross 13, and the concat layer takes the output of the reorg layer, which is 2048 13 13, and the output of this is going to be 1024 13 13. The result in concatenation is 3072 13 13, right? 2048 from the current layer and 1024 from the 1024 from the current layer and 2048 from the reorg layer. 2048 divided by 4 is 5 and 2. So we had 5 and 2 layers there. So we had 26 cross 26 cross 5 and 2. We do a space to depth. We get 13 13 2048. We concatenate this with 1024 13 13, and we get 3072 13 13. Now you can convert this 13 13 3072 to. So what do we have now? 13 cross 3072. What is the output expected? 13 cross 5 cross 25. Can I write this as one and the same thing? Right? And we know how do we convert from this to this. Use a 1 cross 1. Is part clear? So we are not going to convert into 4D. We are going to convert this back into 3D. And please remember, this is not 3D. This is not a 3D information. This is 1D structured in this kept in a 3D storage. Right? Why? Because if you look at block number 5, 4, that block is not related to block number 5, 5. Both of them are supposed to store something else. This guy is supposed to store the information of the object it is looking at, not the what neighbor is looking at. And this guy is supposed to have 5 coordinates, right? 5 templates. So how is the 125 now stored? 125 is going to be stored like this: 1, 2, 3, 4, 5, followed by 1, 2, 3, 4, 5, followed by 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then followed by 1, 2. In a straight line, I'm showing it like that, right? So basically one single long 125. So 1, 2, 3, 4, 5, and these are my objectness parameter: 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 2, 3, 4.
So but when we use 1 plus 1 to convert from E072 to 125.
Correct. So we use, remember in VGG we read we don't use fully connected layers, right? We are not using fully connected layers because we know fully connected layers are really not that efficient. So that is what 3072 to 13 cross 13 converting to 13 cross 13 cross 125, and we use 1 cross 1 cross.
But isn't there a lot of information which you mentioned that which might we could have reduced it and then converted it?
Completely up to you. You can add, instead of this, you can add one more layer, 1 cross 3072 cross 512, and then go for this. I would also prefer something like that, right? The reason why would I prefer something like that? The reason I will prefer something like this is because let's see the network again. This is my network, right? Here I have 1024, right? I have trained this for ImageNet, correct? I trained this model for ImageNet before I did this conversion to 1024, right? This region part is coming after this, right? So this 1024 gets converted to 125, and then we are reading this particular part. Because I have trained this 1024 for classification, ideally I will want one more layer here. VGG is not using that layer. VGG is directly going from 1024 to 125. But ideally you will want to do that, and this is what we're going to learn today also, that if I've trained my model and the model is trained for classification, I should not directly connect it to do box and classification. I should add something in between, right? Because these kernels right now are trained for classification only. Now you're asking something else also, right? This is your accountant. You're certainly asking you to file your court legal documents also. Better would be that we get someone else who can actually handle that part.
But how would that middle 1 cross 1 will help in creating the bounding boxes?
How will?
How will that 1 cross 1 will help in that?
Help. It is not helping, it's just rearranging that.
So it is like same, but it just is asking him to file the legal codes for just adding a 1 cross 1.
Correct.
So why would that 1 cross 1 extra 1 cross 1 will help in that case?
Why would that? Okay, right now we are at 13 cross 13 cross 3072, and I need to be at 13 cross 13 cross 125. How do I do this? See, the role of 1 cross 1 here is not what you're expecting. Role of 1 cross 1 here is to get this number.
So that's what you're saying. Instead of doing it in one step, do it in two steps.
You can do
or
it.
more than.
No, but that has the features of the objects.
Who has the feature? 3072
has the features.
let's see that it has the features of objects. I do 1 cross 1 cross 3072 cross 5 and 125, right? And I get this. What I'm asking here?
Only the important features should come.
No, I'm not asking features at all. There's nowhere I'm checking features here. In 125, what am I checking? What class is it?
Exactly. So
What bonding box is it?
How come the bonding boxes values come from?
One second. What class is it? What bonding box is it? If you're asking this question to this guy, he's going to ask this question to this guy. He's going to ask this question to this guy, which means you cannot keep this layer fixed when you're training bonding box. Which means you cannot keep this layer also fixed. So you have to unfreeze this, you have to unfreeze this. That is what YOLO is doing. YOLO is going to freeze layers before this for classification. For classification, the whole model is trained as it is. But the moment you start training for your bonding boxes, you're going to freeze these layers, and you're going to unfreeze this, and you're going to unfreeze this, and you're going to add this 1 cross 1, and then you're going to train. Right? If you go back to our notes also. After classification training, last convolution layer is removed. Why is it removed? We are training for 1000 classes. Right now we are not doing a bonding box for 1000 classes. And 3 cross 3 convolution layer where 1024 each followed by final 1 cross 1 layer is added. So they're actually adding 3 common layers. Right? Instead of just one, they're adding 3 common layers, making sure that they learn the classification and bonding box, and then 1 cross 1 to finally move it to your how much? 125. Okay. Now this is clear. This.
So we use the same method to identify events where there are multiple objects of same class, like 2 deer. So we are trying to find a bounding box for a deer. So there are multiple names in the image, and then we use the same image for the same network. This network which is trying to identify the box. What will happen?
I didn't get your question.
So we train this network to get a bounding box for an object.
Yes, we are training this network to get a bonding box for an object.
An image comes which has multiple objects of same class.
We discussed that every single kernel is looking at that. Every single channel is going to fire if that object is there.
Multiple boxes.
We'll get multiple boxes. You remember this image from the last class?
But we are getting only X and Y, right? So X and Y
No, we are getting 125 values. We are getting 5 into 25 values. Right? We are getting 5 into 125 values. 5 into 25 values, right? 13 cross 5 cross 25. So each block can actually can predict 5 values, and that is what you're seeing here also, right? You have Barack Obama and he's wearing tie also. Do you see the tie?
That is black.
You see the network hallucinating? Whenever coat is there, tie is there. Okay.
Reason for change in input image size.
Sorry?
Input image size change from V1 to V2.
So you can get to 13 cross 13.
So yeah. Like
13,
what we-
26,
yeah,
50.
So what we want, so that's
Yes.
why I think.
Yes. Okay. Now this I think we covered everything on the loss function. You have any question on the loss function? You understand the new loss function now, right? What is the difference now? We have this ij here, and then we have this summation I to b also, right? And all of these are ij's, right? Let's look at it in a quick way. I have 13 cross 13 and I'm checking for block number 44, right? Cell number, template number 3, right? So I need to check 44. C has cat, and if I made my data set in such a way that I'm saying my cat is here and my dog is also here, then I have to check my C44, C4 for example for dog, right? So I have to check two classes. Let's say there's one more class. I have a dog holding apple also, so I have to check 44 template number 5 for apple also. Now I can't check that if my loss function looks like this, because here it lets me go to block number 44 and check for only one class. So I have to modify this, and the way I'm going to modify this is by adding this 0 to b, and then one object is already there, and I'm going to check for each cell, each template, right? And I have only one Cij, right? I don't have additional Cij, which means this is Cij's. Is clear? Any question on this?
Cij is a cell, right?
Ci is cell, J is template.
So when I have three classes,
Yeah,
so you said that say I fix template 3 for cat,
correct.
and for dog I can't fix the same template. I need to go.
You need to go for some other template. Now this is what? Cell number 44. Where is my Ci here? This is Cij, right? There's no Ci here. There's Cij. So I have to check Cij, which is saying this is a cat, and then I have to check for template number 4, where block number 4, and I have to check Cij of that particular template. And if that is saying there's a cat, then I can actually get the cat coordinates from there. So one block can predict 5 objects.
So if there is a single object, in that case, all of theCijs will tell that there is one object.
No, only one template you can pick
With the maximum.
with the maximum IOU, and that template, let's say, happens to be this one. So this is going to be 0, this Cij is going to be 0 and 0 and 0. Cool. All right. This we covered. This we covered. Okay, so let's start into this session. It's not a long session, but it's an interesting session. Now, disclaimer: not falling into NIH syndrome. What is NIH syndrome? NIH stands for not invented here. Not invented here. There are many startups, many companies which fall into NIH syndrome. Not invented here, we are going to do it from scratch, and then you spend all the time on the scratch. I found this wonderful link for I started writing myself and then got this link, and whatever I wrote was already there. Plus much more better content. So I'm picking content from this particular site. Go there. I'm going to cover some code from this particular website also, right? Very beautiful for transfer learning. One single file, one single page, and you'll get the thorough understanding of what exactly is happening there. Now,
This is not an improvement of those patented techniques, right? BGG or uh,
They are patented. Dropout is patented. Your
so if it
batch
is not
knowledge
invented here, then we will run into issues, right? It's our
not invented here. Patent is not there. Okay. Not invented there here. Patent is there. Not okay. That is why one of the research group of our school is also working on batch normalization, where we are not using batch normalization, completely convolutional batch normalization, and we have got the result which is as good as batch normalization. Without using batch normalization, directly using convolutions only, we have been able to replace batch normalization, and dropout we have anyways don't need. We've discussed that. We use cutout. If cutout gets patented, we are going to use drop cutout. We are going to invent something. So yeah, they are patented. You can't directly use them. For example, if you are running a
okay
startup,
for the transfer learning purpose also.
transfer learning purpose also. You need to be very clear. If you're running a startup, you're copying something from Resident 50 or Resident 34, you cannot use that commercially. You cannot use those models commercially.
For the model DavidNet,
Nothing.
DavidNet also we cannot use it for commercial.
No. YOLO also you can't
We
use.
customize the architecture in this according to our need. Like
Sorry?
instead of addition, we make it concatenation.
Yeah, so if we customize the existing architecture, so still it's like
Adding value.
Answer one simple question. Have you finished assignment 14?
yeah, I mean not reach the benchmark.
That's all. That's where the problem is. That's what I'm saying. You want to change, change. Let me see how you will get the state of art.
No, no. Back to your question, you said that
You
cannot
can.
use for the commercial purpose. That's why I'm
You can
asking.
change.
Yeah.
Yeah, you can change anything. So there's an acceptable change also required. When you go for the patent office, there's an acceptable change required.
Yes.
You are copying the original idea. You're changing something in the original idea, but that still maintains the original idea as the original idea. You can't use it.
But for commercial purpose, we can.
No, you cannot. That's what I'm
So
saying.
nothing, ResNet, ResNext, nothing can be used.
Nothing can be
So
used.
what is the we'll understand the mechanism behind all this. Otherwise, what is the point in learning? What is fast AI doing? They are using the same and
Who's using it commercially? Fasta is not a commercial company
what kind of
deploying model.
people companies want? If somebody was going to recruit, they'll ask about
They will ask you to
VGG.
train the model from scratch and achieve the state of art.
Okay, we should not use the weight, but we can take the model.
No, you cannot. You have to write it from scratch on your own.
What if that resembles VGG or?
Then it resembles VGG. You have to prove that it resembles VGG. You have not copied it.
Unless the you can convince it.
Okay.
But do they have used it? Like let's say the model is applied.
That is why everyone is stealing.
They don't have.
No. AI, if you think about it, is the only field where people are releasing papers with code. Tell me any other field where people are doing that. Not there's no other field where this is happening. And that is why this AI is like running like hell. Only field where people are releasing code, train, model, everything, go use whatever you want to do. This is the only field, and this is the first time which is happening in the history of humankind, where people are actually collaborating for a field to do self-destruction. There's no other field where we've done that, right? Do you think your Pfizer or GlaxoSmith are going to release the actual way they made the medicine and the complete paper of how they tested? This is the only field where this is happening. That is why there's a fad over it, and there's an over availability of engineers who claim they can do stuff, but you cannot.
How is that if batch normalization is not permitted inside the company for any commercial purposes? How will they get the model trained without batch normalization? I don't see.
They are going to use our algorithm APS.
So, what do you say about the libraries where it exports batch normalization APIs?
That's what, right? If you use TensorFlow and you use batch normalization, they're licensing their patent to you.
They are?
Licensing their patent to you.
Which means we
You
can
can,
use.
yeah.
If I'm using TensorFlow, I can use batch normalization.
Yes. If you are using PyTorch, no. So it's going to get complicated. Right now they are not pushing the laws, because then you have a question. I'm using PyTorch on Google Colab or on Google Cloud. Then is it allowed or not? Or maybe I'm importing TensorFlow library, using it with PyTorch and then using batch norm. Then is it allowed or not? The questions are going to come.
Apple and all using, Apple uses ready-made APIs. They must be internally using batch normalization.
Yes, they will be using.
For every batch normalization they use, they are paying Google.
No, right now, that's what Google has just filed a file for the patent. They are saying we are not going to charge, use it, but we have filed a patent. See, patent is like a nuclear weapon. You use it as a last recourse. Patent fight, if you go for patent fight, they use it as a last recourse. That's not the first thing you go for.
So if you're not using the batch normalization API provided by TensorFlow, if we write our own batch normalization function,
No,
then
you
also,
can write it anyhow. As long as you are same as the same batch norm, you can't use it.
it is a standardization of the data, right? X minus mu by sigma, it has been there for years.
Not plus, not multiplied by gamma plus beta.
Okay.
That's what they did, right?
Fast data is used directly, they will not be able to, you can't use those values then.
We can use them. How many of you have downloaded torrent movies? How many of you have downloaded torrent movies? You're doing it.
But we can't tell publicly we watch torrent movies. There's a difference. It is usually, you cannot tell publicly that you're watching.
How many companies have downloaded torrent softwares?
Publicly, nobody.
Everyone. Microsoft knows every single torrent which. So my head of sales is from Microsoft. You met Shrikant. Microsoft knows every single company in India, not only using not Microsoft, but
They can do it.
no. As long as it's not enforced, people are not going to. It's on enforcement. The moment people start enforcing, then it's going to become complicated. Like in US, you cannot use torrent.
So CFN convolutions and ReLU is not patented.
As of now. As of now. And that is what is good about AI right now. That many technologies are open and you can use it, but not for.
There is something which is already open, people are using, they cannot patent it, right?
No.
So it's batch people are using batch normalization for quite some time, then they're not yet.
Proper people are still using, but still they patent it.
How it is possible when people are using, people are patent it?
You release it first. No one else patented. It's still first. For example, in America, people were living in America. Then what is the point of discovering America? Well, Columbus is known to discover America. They were America. He called them Indians. There were people living there, right? Or Vasco da Gama discovered India. We are here for 5,000 years. What's coming from outside? We have discovered you now.
So many startups they launch products. They use like existing AI, this transfer learning models.
Yeah.
So they when they like bring their product into the market, like are they paying back to like these people?
There are so many workshops done on fast AI. People call it, I know, deep learning. Stuff.
Yeah, they do.
What is the point in learning? Someday it's going to be.
Let's look at it. Till now, how many red lights were you breaking? Now, how many are you breaking? How many of you actually thought about checking your car, check for pollution?
If was there, but still.
I already did.
Now you are thinking about maybe some petrol pump, it should be visible, I should get it checked, right? So it's about enforceability. People are not enforcing this, that is why. Do you know that you cannot make a MP3 player without paying Philips or Thomson?
There are so many.
You can't make a phone. We can't make a phone without paying Thomson.
No, I'll give you one easy example. You can't have more than 5 liter memory in your house. As per excellence.
No, I'm talking about MP4. When you're making an MP4, Thomson owns the patent.
But they don't enforce it.
It's enforced.
But others do make.
Everyone who's making everyone who's making MP3 players or phones is paying Thomson or Philips. They own the patents. Otherwise you will not get a license from Google. So everything is linked. The patent industry works very well. Right? Every phone which Apple sells, even if they're using some other 4G, end up paying Qualcomm $20. Do you know 70% of engineers in Qualcomm are not engineers? Like 70% employees in Qualcomm are not engineers. They are lawyers. Qualcomm is a legal firm. It's not a 4G, 5G firm. Okay, back to the course.
Back to that background question. So one of our group is using the without background.
Without background.
So I mean it's recommended. So like understanding the current situation, it's recommended to go without background also. Right?
Recommended to go with background as long as nothing happens.
Any glimpse on what is the typical drive?
We are just finalizing some things. We are trying for this CVPR. If everything falls in place, we will be able to write paper for that. The results look good right now, but we should be able to get the final conclusive results, right? Because as I said, unless you can't train for state of art, you can't. So
then you will be training for patent.
Okay. No, we'll follow Google policy. Don't be evil. Okay. One of the most powerful ideas in deep learning is that sometimes we can take the knowledge of the neural network which has learned from one task and apply that knowledge to a separate task. That is what transfer learning is, right? And this is what YOLO has done. This is what you guys are also going to do in future. And this is why assignment 14 also becomes very important. You know how difficult assignment 14 was. Training another model for that kind of, let's say I start assignment 26 and tell you that now you have to train for ImageNet with that accuracy. 27 a session, no one is going to be there in the class because it's very hard. It's very hard. One parameter change and the whole thing changes. So it's much better to actually pick one domain and then move it to some other domain. Pick one model and move to some other domain. As humans, we also do transfer learning, right? Before you start riding bicycle, I'm not sure how many people rode bicycle first and then tried the cycle. Most of the people knew how to ride cycle and they were easily able to go on the motorcycle. Otherwise, you have to train from scratch everything on motorcycle. Not safe. Right? Yes, no? Yeah, same thing happens in many different fields. Right? If you are a cook or if you cook, you can leverage one technique from one dish and apply it to somewhere also. So if you're a cook, you have done this like hundreds of times. Right? But if you're doing something from scratch, I guarantee you cannot replicate it. For example, if you're not a cook and you somehow cooked some wonderful dish, does not matter how you try, you cannot make that again. Right? Because every step matters. If you are a cook, you know how we make paneer butter masala or chicken butter masala. That's my favorite dish, right? Till the last 30 seconds, it tastes very sour. Either it's going to taste very sweet or it's going to taste very sour. In the last 30 seconds, you're going to add that garam masala and the whole taste changes. Till the last 30 seconds is not edible, especially if you don't like khatta. But in that 30 seconds, everything is going to change. Same for tea also. When you make ginger tea, try this recipe. Take sugar, tea, water, milk, boil it, and then add ginger. You're going to get that non-edible chas. Pura ka pura chai is like literally not edible. Like all brown water and then whole white thing is separated. There's a time for adding that ginger. That is initial period when you boil it, right? Same thing happens for models also. There are steps which have to be replicated again and again for the model, right? Now, let's take that tea example. When I'm making a tea, can I convert that tea, the approach? Can I take the same approach and make black tea as well as milk tea? Yes, don't add milk. The similar approach can be followed. Same thing can happen for deep neural networks also. We are initially going to be making our edges and gradients and textures and patterns and parts of objects, and then finally I'm going to break objects. So initially many components are same. So I can literally use it for some other class also. We just have to figure out how. Now, the transfer learning is not new. Since 1995 approach has been there and people have been following this. But what you are going to see is that in future this approach is going to fall. And the reason people are not going to go for transfer learning a lot is because now I can train the whole model in half an hour. This approach was there because it was expensive. It used to take months. VGD was trained for 6 months. YOLO V2 also was trained for 3 months. Now I can train the whole thing in half an hour, the whole classification, and in half an hour the whole objective function for the bounding boxes. Literally 1 hour it can be done if you know how to do it. So now why people are still using transfer learning? They don't know how to train a state-of-art network.
But for custom dataset, we have to still.
No, we are going to see how we still use transfer learning for custom dataset also.
But then why don't people go for like full training?
Why full training? Because people can. So what is going to happen is you're going to get end-to-end training facility from TensorFlow and all of these guys. Right now what are they doing? They're releasing a paper and telling you that this is how you do it. Later on you're going to get the end-to-end training module from them. You add your data, this is the model, they are going to make sure that this is the Bayes normalization parameter you pick, this is the weight decay you pick, this is the learning rate you pick. That is going to happen, right? You're expecting this to happen. I'm not sure you're expecting now, but after I've said that, I think now you're expecting this to happen. That the model itself is going to tell you, use that weight decay or use those many number of layers. We're just not even 2-3 years away from that.
A lot of startup already doing it.
AutoML is still different. They're going to figure out the whole architecture. I'm saying that you have your architecture, and on top of that, the background TensorFlow is going to tell you that for this particular use this loss function, for your initialization use this initialization, for the weight decay use that weight decay. So those values are going to be automatic. For batch size is this. Right? Same thing we saw in our eager video also. They are trying to figure out the buffer size directly and they can provide it to you, so you can actually do parallelization faster. Now, ImageNet is sort of the mecca of machine learning. Reason is that there are 1.2 million images, 1,000 classes, very, very difficult to train. But once you train any model on top of this, that model can be used for any other class. And while I'm saying any other class, I'm keeping the medical side aside. Nearly every other class is there in ImageNet. Think of an object which you might not found there. Spoon, fork, plastic bottles, wine, snake, tortoise, dogs and dogs and dogs. There are like 120 different kinds of dogs. So really every single kind of texture is already there, which means if the network has learned this, I can use it potentially for something else also, except medical. In medical, my initial data itself is very different. So I have not trained this on medical data, right? But you can think about this approach, right? You collect medical data and you train one model of medical data. Let's say we as School of AI decide to collect 1.2 million images of medical data. CT scans, X-rays, tumor, and TB, and every single X-ray which is possible. And when we train a model on that, that model is going to become the gold model for any other medical exercise. Anyone going for any Kaggle competition is first going to download our data, our model, use that transfer learning for that particular model. Okay. Now, problem with ImageNet is, or the way we are training for ImageNet is, we can't apply the same approach anywhere else. We will not be able to create 1.2 million data set of the medical data. Right? Let's say you're trying to make a car detector. If you're trying to make a car detector in India, you have 300 kinds of cars. Maybe 700 also. I'm just making a number, but close to that should be there. If you have those many cars, you cannot go on road and keep on collecting images of those cars. If you do, what happens? You may go to jail. I told you, right? That happened to one of our School of AI student also. Especially autos. If you take photograph of auto, that guy is going to be very angry, especially if he is drunk. So you can't go on taking a photograph different vehicles, but you can take some photographs. They're on internet. So some photographs can be captured safely without you getting killed or in the jail. So I can't create a database which is like 1.2 million. So I can't expect that kind of accuracy. That is not true. I can still expect that kind of accuracy because I have a model which is trained on objects which are similar to automobiles, and that happens to be ImageNet. However, if there is another model trained by Google or Nvidia for US kind of cars, that model is very close to the model I want. I'll definitely want to use that model, and that is where your decision is going to depend on. Which model you're going to take is going to depend on what kind of data it is trained on. Now, this is the approach we are going to follow. We have the old classifier, we have the old model. We are going to replace most of the components from the model we are using to a new classifier and new data, right? One magical thing which is going to happen here, which I'm going to cover in a moment, is you may not have labels. The data you are collecting for transfer learning, you may not have labels there. Transfer learning still is applicable. Right? Isn't that beautiful? Search Indian cars, I'll cover that. On Google Images, go search for Indian cars. It's going to show you a list of Indian cars. Run a crawler, download all the images. And your network is going to tell you this is Hyundai without a label. This is Ertiga, or this is Jeep, and so on. Right? So we are going to see how that works. Now in traditional learning, you are going to download a data set, train a model from scratch, label it, and then you are going to proceed. In transfer learning, we are going to use an existing model, and then we are going to use that to train the new data set we have. Now this is the official definition of transfer learning.
The training set, the transfer learning you're saying that there won't be any labels, right?
That is not what I said. I said you may have a data set where labels are not there.
Transfer learning, we're going to use that kind of data set.
I'll explain that again. You are trying to make a model for a data set where labels are not there. So you can take a model which is trained on labeled data set and try and work it for the data where you don't have labels. How do we do that? Sorry? No. I'll explain that. How do you do it? I'll explain that how to do it. Now this is the official definition of transfer learning. Given a source domain DS, a corresponding source task TS, as well as a target domain DT and a target task TT, the objective of transfer learning now is to enable us to learn the target conditional probability distribution P, Y, T given XT in DT with the information gained from DS and TS. Are you listening or saying let it finish? Where DS is not equal to TS and TS is not equal to TT. In most cases, the limited number of label target examples is exponentially smaller than the number of label source examples are assumed to be available. Clear? What we are saying here is you are going to use transfer learning if the model size, if the data sets are not same. If the data is same, there is no point of transfer learning. But you are going to use a transfer learning where the data sets are similar. That's all. visually.
Even if they are dissimilar, this can be a starting point.
This can be a
Starting point.
for any model, yeah.
No, I think the textures and the initial layers, right? Those will still be similar for different.
Yes,
So can we freeze them and then train other
that's what people do.
for the if the objects are dissimilar?
Yes,
We can do that.
yes. Okay, now there are three main questions in transfer learning. What to transfer? When we're saying what to transfer, we are essentially talking about which part of the network to transfer. If the objects are very different, but you know edges and gradients are still going to be the basic building blocks, I'm going to just use the initial part of the network. If you know that majority of the objects are similar, like ImageNet versus 120 classes of dog, I'm going to use majority of the network. If I know that it is very similar to my objects which are there, I'm going to use the full network and just replace the classifier. So the amount of data model you're going to use depends on the kind of data you're working with, right? For example, if I'm working on using ImageNet to a cars only data set, then I know that most of the model in the end was working for 1000 classes. I don't have 1000 classes, and my classes are not frogs and hair which are there on dogs. I'm going to keep most of the model same, but the last layers I'm going to change, right? Part of the objects I will like to change. Part of the objects I am going to go for new model or new weights, or I'm going to just delete all the weights, keep the weights there, but make all the weights reinitialize the weights, and then add a new classifier on top, and then train from scratch. Train what from scratch? The last layer and the fine-tuned layer which I'm looking at. Okay. When to transfer? So when do we use transfer learning?
We don't have tangible data set.
You don't have data set, right? You don't have time, and that is what I've seen. Data set is not a problem. Time is a problem. When we say we don't have data set, right? For example, ImageNet also people are using trained model and then training their ImageNet. When you're doing object detection, you have 20 classes, right? We have 20 classes in YOLO. He's still using transfer learning. He's training on 1000 classes and then again collapsing it to 100 classes or 20 classes. So we use transfer learning because of time, because training a state of art network is very difficult. So you are going to be using mostly because you don't have time or you don't have the training hardware. You don't have training hardware, there is nothing else left for you. You are going to use a pre-trained model. What is the fourth option? Difficult in retraining the model from scratch. And what is the fifth model? What is the fifth option here? You don't know how to train a state of art network. We are definitely going to go back to the model which is already trained. How to transfer is what we are going to cover now. Now, there are a few transfer learning strategies. First is called inductive transfer learning. In inductive, what does it mean? Inductive sounds like, what does it mean?
Just by touch.
So when you don't touch and just take to the, generally we use in electricity. When you take an electric object or magnet to a particular socket and you don't touch it, but you induce it, then we call it inductive.
Like in simple English? You gave a physical example. I'm looking for induction. Like when you say, let's say, what is the name? Sherlock Holmes is using the word induct. Like I'm inducing something. What does he mean? What does it mean?
It's not
One form of energy.
the causing it to happen, not actually doing it.
The first one, right? Characterizing by the inference of general laws of particular instances. Essentially inferring by your knowledge. That is induction. Like Sherlock Holmes is known for his inductive things that this has happened because of that. Your hair are yellow, your skin is brown, so you are from Afghanistan, something like that. You fought in the war in Afghanistan. You've seen Sherlock Holmes, right? He can do all of that. And after you listen to him, it sounds like, yeah, that's correct. But you think, and then you look at your skin, then you look at your hair, no, I'm not in Afghanistan. That can also happen. Induction is essentially knowing something beforehand, looking at the information coming in, and then predicting about that. Right? Is that clear? Yes, no? And let me see how you can do induction. I'm going to show you one image. Sorry?
Kind of an intuition, like we know.
Intuition. You can use the word intuition, but because it's a computer, we can't use the word intuition, but you get the idea. Let's say you have not seen this object ever. right? Let's say I've not seen this object ever. And I ask you a very simple question, just say yes or no. Does it look like a tank? Don't say but this. You can say yes, but you can say 0.4 years, 0.3 years. Does it look like a tank? Does it look like a binocular? Does it somehow look like an old tape recorder? Tape recorder or cassette? Cassette. Does it look like a frog? No. Right? Does it look like a dog? No. Is the part clear? Okay. So that is the induction part. Now it is looking like all of those things, right? Now is the same thing true for this? Does it look like a tank? Does EVA look like a tank? This? Which tank? Star Wars tank? Right? It does not look like a tank. It does not look like a binocular. It definitely looks like some sort of LCD. It looks like an egg. So there are some things which are common here, which will always be true for these guys. Now, if I show you one more image, and that image has a tank, looks like a tank, don't think of softmax. Softmax is going to screw up everything. Just before softmax, I'm going to tell softmax I'm seeing a tank. If tank is one of the class, tank class is saying, hey, I'm there. I found many features which are belonging to me. The binocular is also going to say I am there because many features belong to me. And all the other classes are going to fire. I'm going to go to softmax and tell him that I am there because the features are there. What is softmax going to say? He's going to hear the loudest one and then predict. So softmax is going to create an issue. But the class or the layer before that is not doing that. The layer before that is firing for the feature responding. Is the part clear? Is this not true that every time I send this image to my model or send any image to the model, the tank is going to fire, the binocular is going to fire, and all the other classes which were firing will fire? They will fire. Right? And because they will fire, I can use that fact. I don't need to look at the softmax. Right? Now let's look at another class.
So we'll look at those numbers basically.
Sorry?
We'll look at those numbers.
We are going to look at those numbers. Now, if this class is there, if this class is sent to VGG, don't look at softmax, right? What all classes do you think will fire? Dog will fire? Cat will fire? Bear will fire? I think bear most probably will fire more, right? Your monkey may fire. Human may fire, may not fire. I'm really not sure. Sorry? No, don't look at that. Just look at the. You get the idea what is happening, right? These are not trained, right? Now let's look at another class. Tell me another character you know of. What do you think the kind of classes will fire?
Wrestler.
Tesla?
Wrestler.
Wrestler. No, ImageNet classes. You get the idea? Any other class, any interesting class you can think of?
Some bird.
Bird might. Bird is a class which it will fire automatically. Gorilla will also be there, hopefully. Yeah. What all classes do you think will fire for this? Right? Metallic objects will fire wherever metallic objects were there. So in that 1024 vector which directly connects to the 1000 classes, many guys are going to fire, right? And what that 1024 guys say, if you think about that 1024 layer, just before the before the 1000 layer for the softmax, I have 1000 classes, right? Before this I have that fully connected layer connecting 1024 vectors to this guy. Let's look at what this guy is saying. Now, I'm telling you I found this, right? Or let's say I'm telling you I found this. I found that particular edge. I'm telling you I found this particular edge and we are doing alphabet classification. Which alphabet is going to fire? N maybe not, maybe that's the N we have. Is it clear? The moment I tell you that I do not have this, I do not have this, what all can be removed? Anything else? Right? The moment I tell you I do not have this, what all can be removed? I do not have this.
M can be removed and M.
M can be removed.
M and X.
X also.
M.
M, M.
X.
X.
Okay.
N can be.
P can also be.
Okay. Why? Is it clear? And the moment I tell you I have something like this, I have something like this. So V can be removed. If this was longer, it would be V. How do I tell it's longer or shorter?
The activation.
The activation. If many pixels are lit, the value is going to be higher. I just look at the value, right? I have used a gap before that. So the layer would have given me a smaller number for Y as compared to a bigger number for whatever was behind that, right? Is the part clear? So that 1024 layer is not only telling me which things are there, but you realize we need to know which things are not there. This is very, very important. Now, if I have 1000 classes, I am going to use those 1024 vector, connect to that, and that's going to tell me that I am looking at a binocular because the binocular was there. But what has happened here, softmax has come into between, softmax has come between, and that is screwing this up. So we remove this. So we directly look at it 1024 thing. Now what is going to happen is, I have this 1024 vector coming in, I send an image of volley, and that is going to give me 1024 vector which belongs to volley. What do you mean by it belongs to volley? I send another image of volley taken from another angle for another thing. It's going to give me 1024 vector again, and that is going to be similar, not same, similar, depending on how much binocular was visible, how much tank was visible, and so on. Now if I send image of EVA, this 1024 vector is not going to be similar. Is it clear? I'll cover that. Not that complicated, but is this clear? Now what exercise we can do, and I have done this exercise also. I take my resonate 34. Resonate 34 has this 1024 last layer. I send in around 1000 images of 10 classes, so 100 classes each. It is going to spit out 1000 vectors. I take this 1000 vectors, you run tsne, it's going to give you 10 clusters automatically. Why? Because most of these are going to be in a similar domain. You can run k-means also in a complicated way. You can run SPM, you can run PCA also. In all the cases, you're going to see it's actually able to very well structure the information out. Why? Because each of this vector is telling me tank information is there, some binocular part is there, some part of old electronic object is there. So it's going to classify as that one thing. And another class, let's say we are sending in which is not in a database, let's say what? Bangalore roads. Right? You're going to find that they are pinpointed at one structure. All of these are same because they have similar structure. All of them are black, and there's a hole, there's water, and so okay. You get the idea, right? Okay. So inductive transfer learning essentially means that I can use an existing network which has learned on something similar to the data set I want to work on and use the model from there. But read the last line here. Depending on whether the data set contains labor or not, this can be further divided into multitask learning or self-taught learning. Now let's see what do we mean by this. Depending upon whether a dataset contains label, if the dataset contains label, it's called multitask learning. Why do we call it multitask learning? You're expecting same model to work for ImageNet database, and you want the same network to work for your cars database also. So multitask, if you think from the model perspective, you're changing only maybe a slight change are there in the model, but essentially you're using most of the model which is there. Final layers you might be changing or not. So that becomes your multi-level, multi-task learning. Now second thing is what? Self-taught learning. Now what is self-taught learning? This is a data set and is huge. This is another data set and that is small. One of the reason we use transfer learning, right? Now we take a model M, right? We train a model M on this particular data set where labels are there. Let's first take the labels are there. L1 is there. If the labels are there, I'm going to get a very good model which can classify between these, let's say 100 classes. Yes, no? I know that this data set is similar to this data set, that is why I'm talking about this model, right? Then I'm going to use this particular model which I have trained on this data set is going to give me, divide the data set into this and this, some classes, task is done.
This classification is for the labels which we trained using model 1.
No, we just discussed that 1024 vector thing. We have done that, it is giving me 2 clusters. This is the model which I have trained for the dataset. I know the dataset is large and it's called labels are also there, so I can train it very well for the 100 or 200 classes, whatever is there. Now this is another dataset. In this dataset, I don't know how many classes are there. It can be 2, it can be 3. Let's say there are 3, but I don't know actually, right? I'm going to run this model on top of this, and it's going to give me some vectors for the whatever images are there, and I'm going to use SPM or tsnm and cluster them. It's going to give me these clusters. Our task is done.
But no labels, right? Like,
No labels, yeah.
But I might not get 3 labels. You can get anything. When we do this thing, I might not get 3. I can get whatever, depending on the similarity.
That's right. I started with 3.
But it will not tell what those labels are, it just tells how many number of labels there are.
No, it will tell you exactly what image falls in what label. It does not know what the label is.
no name for label, but it's a basic category.
Category.
So it's we are just doing clustering of all the vectors, that is 1024 vectors. Segmentation is happening.
That's all.
There is semi-supervised learning kind of.
This is semi-supervised, you can say.
Okay, it's only grouping, still labeling is not happening.
Yeah, and if you think about that, what is a label for a computer?
It's an
Any label.
Label for a computer is 0001000. That it has done already. You have not labeled it. Computer has labeled it. The task of the computer is done. Now the question is how accurate the network is. How accurate these images are. And you cannot check.
I didn't understand arrow between these two circles. Here we got 3 of them using
This
the same
arrow,
model.
this arrow you don't understand? Which arrow?
This arrow and the arrow which going to these 2 arrows.
Now is it clear?
Huh? So
Okay,
we
okay.
did
This specific model M,
yeah,
we are going to train this model on this data
label
set,
data set.
on labeled data set. I know that this data set and this data set are similar, right? I don't have labels here, I have labels here. Because I have labels here, I can train my model on top of this and know that my model is 99% accurate or 98 or 96% accurate. Very high confidence on the model. And I know this data set and this data sets are similar. I'm going to use this model on top of this data set and I'm expecting it to give me some clusters. By the way, I don't know how many clusters should be there because the labels are not there. Because the labels,
For every image it will give us what is the class name.
I can't hear.
For every image in this unlabeled data set, it will give what class it belongs to. With that model.
That's, if the labels are not there, it cannot tell you what class it belongs to.
It can, but the model will tell what it is. Right?
No, labels are not same, right? These are not same labels. I'm not saying that I have Hyundai, Maruti and so on and so on and I have same Hyundai here. That is not what we are saying. The models look similar. Let me take an example. This is trained on Indian cars. This is trained on Indian cars, right? Now I want to use this on Ferraris or let's say all the racing cars not found in India.
Okay.
And I don't know which image is what, right? But because my network can already identify between Jaguar F-Type and Audi A8 and Audi A6 and others, it has a very good understanding of how the cars look like. So I can take this data set, I don't know how many labels or how many classes are there. I'm going to run my network on top of that. I'm going to get those 1024 vectors, and I'm going to look at SVM or other kind of clustering, which is going to give me the clusters of this set. 2 points. Point number 1, I do not know the names of the labels. Computers never know the names of the labels. They are just telling you this is 010001. So it is your task to label it. Right? You're not expecting the computer to go model to figure this out, go online, look at the Ferrari, and then do a Google search and come back and tell it's Google.
SVM will expect label, right?
No, there's no label.
But SVM as a technique will expect label.
SVM is still going to give you a number. That number happens to represent a label.
No, SVM has
Zero one or
that label we should have given it, right?
That is what network is already giving you. That is what SVM is giving you.
No, that I understand.
Just giving the description of each category, right? It's
Yes.
giving the description, but it's not giving the name.
No, it's not giving you the name, and it's putting them in the same folder.
Group of features. And when it's actually clustering, there should be some threshold for the similarity, right?
Yes.
Now, if that threshold changes, the number of categories
It will change. It will
If
change.
the threshold is less,
That's the problem
there will be
in
more.
SVN or PCA, and that's why I said you use TSNE.
SVM, not SVM.
If you use TSNE, then it's going to automatically figure out what the threshold should be.
Okay, then that is.
This can help with
It's just like a group of features.
It is a group of images. It's telling you these images are same, these images are same, these images. Based on the features, yes.
Can you just give a good example when you're looking at some entire monarchy? I want to, within the monarchy, I want to do a cluster, which is Swift, Alpha, and all that. This will be a good example to do that.
Yeah, good enough to do that.
Okay.
Now the point on the label and this thing is that if this cluster, let's say I give this cluster name 1, this cluster 2, this cluster 3, right? And this happens to be Audi, this happens to be not Audi, they're not. So this happens to be Mercedes, this happens to be Ferrari, and this happens to be F1 cars, McLaren.
So how do you know the number of clusters?
Let's say this happens to be Mercedes, this happens to be Ferrari, and this happens to be McLaren. Next time you run the same thing again, it is not guaranteed the label 1 belongs to Mercedes. Label 1 may belong to McLaren and label 1 may belong to Ferrari also. That is why the labeling has to be done by you guys or humans for us to figure out what actually is. Second thing, I cannot figure out the accuracy of this model. Because if I have to figure out the accuracy of this model, some human has to sit, or you have to run a model which is already trained on this data set, which defeats the purpose of doing what we are doing, and then figure out. If you can do that, and the way this happens in a real life is you're going to be sampling some images from this. Some images you're going to be sampling, that image goes to this network again, and we are forcing this guy now to belong to this particular category. That can happen, and this is something which we do also. You're not going to train the whole data set, but you're going to train some images to make sure that some layers can be trained. But as soon as you enter the training part, you know that things are going to go out of your hand. Sorry.
How do we know the number of clusters?
TSNE is going to tell us. TSNE is going to look at a cluster, right? See, if your model is good, your volley is always going to get in this range, right? If you are sending now EVA, that is going to get in this range. TSNE can figure this out. But let's say you are sending this to Mini Cooper. These are 100 images of Mini Cooper, and this is 100 images of Mini Cooper S. Those are going to be on top of that. What is the difference in Mini Cooper and Mini Cooper S? 1 centimeter. Not sure on the dimension. They look exactly the same. Exactly same. One is slightly longer, one is slightly shorter.
So let's say if those racing cars, like, of course, they wouldn't have the same design every day, right? Let's say Ferraris, they would have different designs, maybe similar to McLaren and something. So then, how will it be able to actually differentiate those images based on the features? Because features might be related, right? The main features, when we see the images, like, except the logo, everything will be same.
No, I mean, no.
They would have tires, they would have that kind of shape of body. Like the normal images which a person without knowing those brands, right? So how will the network be better than these?
So I say make more easier. Rather than doing Ferrari McLaren, if I have to do bigger Ferrari, I have multiple types of Ferrari.
These are the McLaren cars till now. What are the common things you're going to find? And
Color, planner.
Logo.
you have already identifiable features. Now, same Vodafone sticker in same other car being there is very unlucky for us.
This is not like something which needs to be done by a network, a deep neural network. It can be done through OpenCV algorithm also, right?
Not at all.
No. Why? Current detection is possible, right?
Okay, OpenCV. What is the bonding box for a detection?
Bounding box we wouldn't need, right? Like
You will need, right? Which red color are you going to pick? How much of that red color must be
we can
there?
do that thing, right? Like the one which you told earlier, that we can actually make our own filters.
And that filter is made by deep neural network.
But that will be very, very effective. Like we don't have to.
We don't know. I checked it only on 2 classes, but when we are talking about, you yourself are saying most of the cars are same. If most of the cars are same, then we may fail there. Deep neural, there's nothing. No one can beat deep neural networks today.
So EVA is possible if we detect objects but without saying what it is. So this is going there.
No. This is transfer learning. So what we are talking about right now is that we can have the self-taught learning also, where you do not have labels for a data set and you still want to classify it. Essentially, okay, this is something which you have seen on your phone also. How many of you have iPhone? I'm not sure if the Android phones have this feature or not, but on iPhones, your phone is going to go through all the images you have, and in your folder is going to say same person. Please label it. That is what it's doing. It has never learned on those faces. It's learning on some other facial database. Using some existing facial learning database, it can figure out, okay, all of these are giving me same vectors. So it is as good as what Apple is doing right now already on your phone. So you already are aware of this. Is the part clear? Now let's look at the second problem. Self-taught learning, depending upon whether a dataset contains label or not. So self-taught learning would be that you're teaching yourself that this looks similar. What Apple is doing on your phones right now. Right? We are going to look at another scenario where we don't have both the labels. Now second is unsupervised transfer learning. The source and the target domains are similar, but the tasks are different. In this scenario, label data is unavailable in either of the domains. We do not have labels in both the domains, right? And best example for this is reinforcement learning. In reinforcement learning, this is the scene the car is seeing. This is what you're seeing right now. What all labels should be there? Do you know the data for reinforcement learning for autonomous driving? There's no label required. What would the car do by knowing this is a headlight and this is a traffic light and this is a pole and this is supposed to be a light? What will it do with that?
There can be semantic meaning to it, right?
No. Semantic meaning is on the 3D part, and the way we collect data set for cars also. Right now, for example, let's say we have just 1000 hours of data set. Just 1000 hours. 1000 hours of data set means and the Uber and Lyft and these companies have millions of hours of database. If not millions, at least thousands of hours of database, hundreds of thousands of hours of database, right? So you're going to multiply this with more zeros. You see the number of frames we have, right? Each frame takes $0.5 to label. How much money are we talking about? And that is just Uber, then Lyft, then Ola. I'm not sure Ola is doing or not. Google, Apple is already doing it. That means around $500 million they're going to spend on labeling. Do you think so?
But it has to be sensitive traffic light versus green. It's going to be.
So I'm taking a very extreme example. For example, there's a lamp post, there's a fire hydrant. You're not going to take any annotation for that. Or imagine India. What kind of things you find out next to the roads? What all will you label? Right? Will you label how many kinds of three-wheelers we have? We have those. You have this thing also which has 3 wheels, right? There's one wheel here and then you have 2 wheels. So there are many classes which are going to be there. So what happens in reinforcement learning is, this is how your scene looks like right now. This is the car is going straight ahead. It has taken the decision now that it has to go ahead, right? In reinforcement learning or when you drive also, you take a decision, then something happens. You don't take decision at the moment. You take decisions prior to the event and then something happens. You have taken a decision to go straight and you hit the wall. What are you learning now? When a wall is in front, don't go straight, do something. So it's going to go right. What happens now? again hits something. So now it's learning that whenever this thing is there, that thing is there, don't do that. Now it's going to take this left turn. Where should it take the left turn? There is a pole here. It took the left turn, again hit something. We are not telling the labels, we are just telling what happened. So in reinforcement learning, what you're going to do is you will have policy number 1 followed by policy number 2, go straight, policy number 3, go straight, policy number 3, go right. When you took the policy number 4, what happened? You got a reward of minus 300. So you're not going to take the policy again. So you're going to say my policy needs to change. Policy is to go straight, minus 400 again. Don't take this. Policy is to take left, better policy. Policy is to take left with 10 meters. You hit something again. You don't do that. So this, and what you're going to do, because you took the policy here, this is your label. Reward of 1, reward of 1, reward of 1, reward of 100, let's say, because you took the successful left turn. This is your label. You cannot think of label as something which is attached to an object. Label is a concept now. How good have you behaved is the label now. So it is wrong to say that reinforcement learning does not have label. These are labels. You just change the name of these guys to rewards, and then you can say that these are different things.
But this cannot be transferred across different conditions.
Sorry?
This cannot be transferred used across different conditions.
Yes, now let's come to that. Now let's come to the actual point where we're saying that the source and target domains are similar, but the task is different. In this scenario, label data is unavailable for other domain. Now let's look at one simple scenario. I've trained my autonomous vehicle in San Francisco. Can I drive this autonomous vehicle in Los Angeles? I'm not well with the states, and I'm not sure I've said the city in a state or not, but New York, safer. New York? You can, right? Bangalore? No. But if I've trained my model in Bangalore, can I drive my model in Hyderabad?
Yes.
I still don't think so, but yes.
Bangalore is much better.
Have you driven in Hyderabad? How many of you driven in Hyderabad? What I have observed in Hyderabad is there's a traffic guy standing on his phone. There's a traffic light standing alone, blinking whenever it wants to blink, working properly, but no one is looking at that. These guys are going to decide that it is our time to go, and everyone is honoring that. No car will move. Now suddenly this guy will decide, ho gaya bahut. I am going to go now. And at that time, these guys will honor that. It's magical in Hyderabad. Somehow there's a collective intelligence where people decide it's time to stop and everyone stops, right?
Bangalore is also there.
No, Bangalore.
Some of the places there is no signal.
Everybody will go first.
If you stop at the signal and say stop, that will happen, but in Bangalore traffic is. When there's no signal, when there's no drop, then it's okay.
Okay. Now, what we're saying here is the source and the target domains are similar, but the tasks are different. Right? The source and the target domains are similar, but the tasks are different. Can you give me some example of this?
Like a robot or a car, like let's say.
You can say that, yeah. Right? There's a robot you have to train on Bangalore. If you have trained a car in Bangalore, most probably robot data will also be useful. You may be able to transfer the learning to a robot also. If the robot happens to have 4 wheels and then of equal size in Bangalore, but in US you could have said simpler things. If you have an autonomous vehicle, that data can be transferred to a robot and then it can be trained. We still don't have any label data. Drone may not be, because a 2D to 3D we are transferring. In terms of images, what can you think?
Detecting malicious activity.
Correcting?
Detecting malicious activity from a city scene. Maybe highway and cross, like a busy street.
What are we doing right now? Source and target domains are similar. So you have to think about source and the target domains, the domains in which you are trying to solve the problems, but the tasks are different. So from this source, you are doing something else, and from this source, you are doing something else. But still, the transfer learning can be useful. I wanted to think of this kind of an idea. Image captioning. What is the source here? What is the source here? We can, but we need labels for image captioning.
Maybe traffic light in a like street kind of environment and like toll text kind of system.
You come close to a good example. Let's say these are traffic lights. Right? I train my model on top of this. No labels are there, but I can figure out easily in this, right? Which light is what, because clustering is going to give me a very good idea of what class is where. I can use the same data on a robot where I have two lights of this color and this color.
So at the end of the clustering, you're going to label it. You're not going to let it roam.
In the end, we do that.
Okay.
But it's fun to say that there's no label. That's all.
Okay.
So, one example, pose detection versus driver distraction. So, see the poses I will take in a retail perspective, like different poses, and those poses I will try to make use in a driver distraction.
As long as somehow you're saying labels are not there, what you're saying is correct. Somehow, as you see, right, if the labels are not there, I can't solve this problem. So it's a fancy way of saying labels are not there, but someone has to go there and say the labels are still intact. Okay.
And Rohan, why giving extra examples is a problem. Like you said, if a model is trained in Bangalore, it cannot be used in San Francisco. So here, we are making, like, of course, the environment is different. Let's assume the environment is same. So is it possible?
If environment is same, everything is possible.
No, I mean, as in, like, the left and right time is same.
Sorry?
Like, in India we move left, or in, like, USA we move right. So only if we accept those two things, like, we are not considering that.
You've been to outside country?
Yeah.
You've seen the laws there, how people drive? None of that is followed here, right? How do the roads look like in India? I'm drawing a very good quality road. This is how roads look like in India, right? And this is how we do it. And this is actually like we have 50 feet road followed by 150 road. So there's this also. How the roads designed in US? Let's say you have this road here, right? If you have to take a turn, this is additional area which is left, right? And the front guy is, how should I draw? So this guy is going to come from here, go here, and then go here. And this guy, yeah, something like that. Yes. So these guys are going to go straight, right? Whosoever is coming from this side, they skip to another lane and then they take a left or the right turn. Same thing happens from here also. There's additional space left for people to take a turn, right? Not in India. In India, we have like everyone is in front of everyone. So laws are very different, right? We have a law in India wherever we have a speed, wherever we have a flyover, we have to have a bus stop there.
We are lucky that it is not on the flyover.
These are some of the laws which we have. Another law which we have is that just after the red light, we should have a bus stop. So you are waiting for the red light to become green, you move there and in front of there you have a bus stop. These are some of the laws we have. So laws here and in US are different. So a lot has to change. But US and other cities will not. You can say US and UK. There what you're going to say is correct because in UK you have the right driving as in India and US you have the left driving. So there it is going to be similar. But if you're transiting from India to, even China is much better. Right? Even China is also following international laws for rules for making the roads. Now let's finish this. Now, the last thing we have is transductive. There is similarity between the source and target, but the corresponding domains are different. The source domain has a lot of label data while the target domain has none. This is what we covered. Transductive. Trying to induce some, the Ferrari McLaren example is actually fits this example best. That you have one domain where you have lot of label data, from there you learn and then you do a zero shot learning or what we did for 1024 vectors and directly implement in another domain.
What is the difference between self-taught and this one?
Repeat that.
Self-taught
Self-taught.
and transactive.
Yeah, so transductive is sort of inductive only, but it's slightly different manner. So what you will want to remember only is transductive and supervised. Because for us, transductive is a part of inductive. There's not a lot of difference. Unnecessary you are getting into GRE and then pushing the two things apart. Inductive, intuition. Transductive, transformational intuition. So what essentially we are going to do, we are going to take a model A and we are going to move that model A to a new target source and we want to solve that particular problem. Now off the shelf training as a feature extractor. Now this is one of the very basic approach. In this approach, you're going to take a model, you're going to throw away the last fully connected layers as I said, you're going to use those 1024 vectors, run SVM on top and you're done. No training required at all. My resident 34 looks at Wally, is going to come back and tell me I'm seeing a tank, I'm seeing binocular and so on. I'm just going to use those vectors, use t-SNE or a very good what is it called, clustering algorithm, and it's going to cluster and that is good for me. Can I test is it correct or not? Unfortunately I can't. But that is already going to give us very good data. Why is it going to give us good data? Because we have made sure the domains are similar and the model we are using is very well trained.
But then we can also go for supervised learning after that.
Then it is not this topic, off the shelf pre-trained model as a feature extractor. Then the topic is the next one, and that topic happens to be fine tuning. But before you look at fine tuning, look at what happens here. What we have done here, the green one is the state of art. The pink one is the CNN off the shelf. We are picking the off the shelf network and then using that. The red one is CNN off the shelf plus augmentation, and blue is a specialized CNN. Let's forget the specialized CNN for a while. Off the shelf means resin 34, resin 50. You're just downloading the data and downloading the model and doing some sort of fine tuning. What you see here, if you train the model from scratch, you're going to get it somewhere around 71.1. But look at where your red guys are. And this is true for every single domain. Every single time you take a model train on ImageNet for a bird classification, the data set trained, the model trained from scratch on the bird data is going to fail. It's going to be losing then the data than the model trained on the ImageNet. Can you wrap your head around this? You made a model which is trained on 100,000 images of McLaren or Ferrari cars. I'm taking a model trained on ImageNet and I'm training on the same data you have. My model is going to be better.
Because of that, whatever this thing is not there in the data.
Because
These features are not in the images, and the model that I have trained only knows about the things that have been trained.
And in your validation dataset, something might come which has never been seen.
Is it because of the noise which other labels might get in?
You're calling it a noise. I like to call it as additional information. I don't think as a noise, right? So imagine this thing, right? You are going to read this particular book and write a particular exam. You have got tuition for this, you have got double tuition for this, you have got triple tuition for this, your mom, dad also asked for this and this only. You are very well trained for this particular exam. Here is this guy, he's going to read the same book, but he was also an IS officer. He also happens to be in ISI Calcutta, and then he's going to read that book. Who do you think is going to win? I'm not sure you've heard of ISI Calcutta or not. Indian Statistical Institute. Indian Statistical Institute takes around 20 people every batch. Only 4 to 6 graduate. People who leave, who are thrown out of the college, join IIT. Not kidding. That is how difficult this ISI is, Indian Statistical Institute, right? Now, if these guys take the exam, they already know such a background that they have multiple ways of looking or extracting a similar thing which you are trying to extract. Same feature which you are trying to extract, same component which you are going to build, they've already figured out long time ago. All you are seeing right now is, for example, those red tires, right? Those black tires, and you're going to be learning on top. But a network which is trained on ImageNet saw red tires, saw your lenses for your camera, saw many circular structures, and they have much better model to figure out all the dimensions and all the types which might not be available in your data set. Right? Look at the disadvantage of what we just said. We said we have 1 million images of McLaren, or basically F1 racing. Look at the other model. It looked at 1 million images of these which you are looking at. Along with that, 1.2 million from ImageNet also. So that guy had extra coaching. He was being trained for quite some time. Because he was trained for quite some time, you're going to see that it's going to be affecting, right? So this is true.
It should be true also for medical domain in some case.
Sorry?
Medical domain also, although the ImageNet doesn't carry those features, but still those, like, something additional information can be used.
Maybe. I'll not like to say yes there, because even the basic features are also very different there. Medical images are mostly very fine-tuned tubes of your blood, right? They're very small. They're very different structure as compared to the pattern we are trying to find. So maybe for different medical domains, some may fall into same category, but I'm not really sure.
It is more fine.
You're talking about literally the first few layers then, and those are the easiest layer to train. So when you want to do a transfer learning, you want to take the bulk of the load and transfer. Otherwise, the going to a layer model, taking the, it's very difficult. Okay. Now fine tuning off the shelf pre-trained model. What do we do here is we are going to take a model, right? We're going to throw away the fully connected layer and replace it by my fully connected layer. That's all. And of course you have to add your loss function accordingly, right? So what you are going to do in this case, let's say we are looking at VGG. VGG is going to add 7 cross 7 cross 512, right? After this we are going to have, let's say, 4096, right? And again 4096, and then we have this 1000 classes. When you're going to take VGG and train it for your own network, you're going to throw away this, this and this. You're going to add your numbers and your classes, right? You have to unfreeze this also. Ideally, you like to unfreeze that also. Okay. Now, freezing or fine tuning. Let's look at the differences there. Now, when you're freezing, what do you mean by freezing? In back propagation, weights are not going to be changed. And when you're saying fine tuning, what do you mean? They are allowed to change.
But a little. But
No.
it's unfreezing only.
Sorry?
Fine tuning means unfreezing. Unfreezing.
This is VGG. Okay, we threw away some of the layers and we decided to fine tune this, and we decided to add our own layer from our own pocket. So these were not there. This is not 4096 which were there in a network. This is 1000, and then I'm connecting it to 10 classes I have. This is what? Frozen. Frozen means back propagation ends here. It does not go back. These 1000 are initialized where? Initialized using Xavier, Glorot, Hey, Kiaming Hey, whatever initialization we have, right? So these 1000 weights are initialized with random values, right? These are not initialized. These are kept the same, but they are allowed to be trained. The benefit of doing this is that many of the parameters are already there where you want them to be. You just have to nudge them slightly. So instead of nudging them from scratch, we nudge them from where they are. So slight modification can happen and they can actually start working better. And these 1000 have to be trained from scratch, because earlier this layer or our 4096 layer was working for 1000 classes. I don't want that. That has changed now. So because that has changed, you're going to replace the structure. And you're going to see this in a lot of companies also. In fact, a lot of ministries also. The moment the minister change, the whole cabinet changes. Police guy doesn't change, secretary doesn't change, right? Most of the staff, IS doesn't change. They do change, but for today you can assume they don't change. Is it quite clear? Right? The whole government system below is not going to change. All of these guys are going to change. This you're going to see in big companies also. The moment the CEO is changed, he's going to get his own secretary. He's going to get his own team to work with him. But the bottom guys are still going to be the same. Accountants and the coders and programmers, they're still going to be the same. So same thing must happen in your DNN also. Why? Because they speak a different language. You want them to be compatible. If you want them to be compatible, you want those to have very good relationships. And that is why we are going to be, whenever you're going to change FC1, you're going to be fine tuning this also. Again, something which has to be seen in real life as well. Right? This is a new minister coming in. He got his own secretary, he got his own peon and maybe driver and maybe someone else. Let's say ABCD. Cook. He got his own cook also. Right? And this is a secretariat which was there since beginning. Now these guys are going to talk through these guys to this guy. Let's say they are rigid. This guy is rigid. Rigid in terms of, he was told by the last MP that at 5 AM I want tea. Simple task. If he continues to do that, what is going to happen? He'll be fired. The guy doesn't wake up till 11 AM. So they have to be tuned now. So the last layer, which is existing already there, you have to fine tune them to adjust to the new expectations, right? Same thing happens in YOLO also. In YOLO, we are ending at 13 cross 3072, right? And then we are doing what? I'm using my 1 cross 3072 cross 125, right? This is going to give me my 13 cross 125. But this is when we started doing the bonding box part. Before this, what were we doing? Classification. I had what? 1 cross 3072 cross 1000, and I was getting what? I was doing gap, let's say. Let's make our own network. We were doing gap and then we were getting 1000. or maybe we are doing gap here, and I was using 3072 cross 1000, and that was giving me, this looks better. We're going to do this. So we were doing this, right? Now, if we are doing this, what is this layer designed to do? Classify. This layer is designed for classification. But the moment you start doing this, you can't keep it frozen. You have to unfreeze this layer and you have to fine tune this, right? Now this guy was in talk with the last layer, and that last layer was also designed for classification. That has to be slightly relaxed also, right? That has to be slightly relaxed also. You're also going to be allowing that to be fine tuned. Is the part clear? They'll also be unfrozen.
So when you're training here for the bounding box, don't you care for the classification loss anymore?
Classification is also there. That's why we are not changing the whole network.
So that time the weightage on the classification loss will be less.
Will be less.
So normally we only just unfreeze two elements to layers.
Yeah, that is the ideal way of doing it.
So why not elements 3 or like we
Because then there is no limit to the greed. If the domains are similar, then this is fine. If the domains are not, we are going to see that example. Now there are many pre-trained models, and in that pre-trained models we have in computer vision, VGG, and similar. Similarly, we have many pre-trained models in our NLP as well, right? Now transfer learning advantages, I don't have to go into this. We have been speaking it for quite some time. Now what we are going to do, we are going to go to this particular link, and we are going to discuss some of the case study which this guy has mentioned. You were saying something?
Yes, that if I take the engagement model and train it on 128 species of dog.
Okay. This is this example. Okay. Now image classification with data. So as I said, this blog is very good. Please go back and look at this particular one. Now the main objective here that we are doing a cat versus dog here. Now in this case, the first thing we are going to do, like all other blogs or all other initial enthusiasts, is we are going to write our own network. So we write our own network. First of all, the data set is prepared. We are going to convert that data set and classify them properly. We have done our separation. We have done our one hot vector and what all. After everything is done, we are going to write a very simple network. Let's say we write the best network to our capacity. To his capacity right now, he's getting 72% as the accuracy, validation accuracy. But we have not done image augmentation, we have not done any other things also. So let's say we do that also. We are adding regularization now. When we add regularization, we are adding dropout. We added dropout, and then we see our network accuracy has slightly increased. Now it is 78.4. Then we see we can do more. What can we do? We can do image augmentation. We do image augmentation, and then we are looking at the model again, and finally we are at accuracy of somewhere around 83.4. Right? So this is the best we are able to go at this point. Now then what we do, we actually use a pre-trained model. If we take a pre-trained model, we are using VGG here, which is called Visual Geometric Group. Now VGG 16 is what we have picked, and this is how the architecture looks like. We don't have to go inside that. These are the three ways we can use it. We can use directly the first, right, and hope that it tells me dog and cat. Dog and cat are classes there, but there are many dogs, there are many classes. I can't literally use that. I have to do something in the end. Second, I'm going to freeze every single convolution layer, and I'm going to unfreeze only the fully connected layer. And third one, I'm going to allow the fine tuning to happen for the last two layers, the last two blocks, and I'm going to freeze everything else, and I'm going to add my fully connected layer, and these are my fully connected layers, which means I'm going to be initializing them from scratch. Right. Now we take the pre-trained CNN model as feature extractor, trainable, all are false, right? Till the flattened, all are false. This is the old one. The validation accuracy right now is somewhere around 89. We have not done anything. No image augmentation, no regularization, whatever inbuilt is inbuilt. The model starts at 89, right? Then what we do, we are going to take the pre-trained model, which is feature extractor with image augmentation. Now if we add image augmentation here, same image augmentation takes us to 90% now. And see what happens when we actually use the pre-trained model with fine tuning and image augmentation. Fine tuning as in we are allowing those additional layers to be trained. Now if we do that, first of all, how do we add layers, or how do we actually read the layers? Set trainable equal to false, set a parameter essentially. You make the whole model trainable. Go in a layer, for the layer in VGG model.layer, you are reading a particular layer. If the layer name is this or this, set trainable equal to true. That's all. What you have to think about a model is that it's like a Python object, right, or a JavaScript object. If you work with JavaScript, it's like an object. So it's going to have a name, it's going to have some sort of property. You're just setting that property true or false. That is how all the models are. And in fact, I should have shown you that part also. Okay, it's about to come. Yeah, look at this. How do we actually do transfer learning? You define a sequential model. Why sequential model? It's VGG. We don't have to go for functional API. But if you want, you can go for functional API also. So I'm going to define my model or add VGG model. When I've done that, I should have said somewhere, it's not shown here, but generally we are going to say that top equal to false. When you say top equal to false, that means don't use fully connected layers which are there in the VGG. If I do that, I'm going to get my VGG model. I'm adding a dense layer, dropout, and dense. Right? This is what he did in initial step. He got 90%. Now, then when we are using a pre-trained model, I'm setting some of the layers to true for the training, which means that that part of the model is not trainable. So when I train my model, that part is going to be fine-tuned. Now, when that happens, see what does code has changed. Till the block 3, everything is false, but after that, everything is true, which means now I can train my model. Now, if I train my model, what happens? The accuracy jumps to 96.2% now. You train from scratch a model and you went to 84, 85, and you take a model which already trained, and within 100 epochs they're at 96. So this is why it's very effective. You'll never be able to train a model from scratch as compared to what happens here. Why? Because that model is already trained with the best of the hyperparameters, which you will have to find for your own model. And that is why it is very difficult for us to.
We can use transfer learning in assignment reporting.
No, because Dawn benchmark is not transfer learning. Okay, now see what we are doing. Evaluating a deep memory. Okay, this is evaluation part. We don't have to go in that. This is case 2, where we are doing a multi-class fine-grained images, basically those 128 dogs, right? So main objective is to go look for the Stanford dogs. We have, this is a Kaggle dataset, 1000 labels for 120 classes. Now, what we are going to do, we are going to pick, I think he's picking GoogleNet here. Okay, this code is to look at how the dogs look like. Then we are going to build a data set, nothing useful till now. Then we are going to look at a validation data set, split a validation data set. The main code starts here. We are going to pick GoogleNet Inception v3. Now, how are we going to link it? Again, we are going to, this time we are going to make a functional API. Why are we going to make functional API? Inception is functional API, right? It has parallel connection. So we need a functional API. So base inception is equal to inception v3 weights. I'm picking my ImageNet weights, right? Sometimes you're going to find your CIFAR 10 or CIFAR 100 weights also. So that way your Keras or TensorFlow will know which model to pick. You're picking that particular model, you're saying include top equal to false. What does it mean? The fully connected layers are not picked. So now you only have the convolution layers with you. Now you're saying input shape, whatever shape we have, out equal to base inception dot output. That's the output of the network we have just copied. Out equal to global average pooling. Out. We have taken a global average pooling. Why? Because the final layer which I am picking right now from GoogleNet is 8 cross 8. I'm using a GAT converts that into 512 channels. I'm using a dense of 512, and finally, total number of classes I have. You take this model, you train it from. Okay, have I said anything trainable? Have I said anything trainable? Have I said trainable equal to false? Where is it?
Only if you want to freeze frame, but not anything.
Cool. Okay, we're not training, right? Okay. Now see what happens. We go to at accuracy of 81.44. Is that clear? However, if you go to the same model and set the last 2 layers trainable, like what we did there, you are going to see a jump of around 5 to 10% here. Add image augmentation, that takes you to even higher accuracy. So you see how easy this is now, and that is what people are doing on Kaggle and other competitions also. And because it's transfer learning is allowed there.
Don't allow for transfer learning.
Where?
In Kaggle.
Some competition do, some competition don't. When you're doing object detection kind of competition, the transfer learning is the only way. All right, so this takes us to the end of the session. Okay, assignment is very simple to read. Assignment is use resident 34, not 50. I'm going to change that. Use resident 34. You can use resident 18 also if you want, but you should use resident 34 because that is going to throw one difficult problem at you and you need to think about that problem. Use a resident 34 pre-trained model on ImageNet. Clear? Same thing what you did. You're just going to copy that from Keras for CIFAR 100 dataset. You're not training from scratch, so it should not take a lot of time. Describe the strategy which you will use. What exact strategy are you going to use? Are you going to freeze all the layers, add your own FC layers and then train it? Are you going to unfreeze some of the last layers and then going to train it? How many layers are you going to unfreeze? So all of that strategy is something you need to write, train, submit the code. Right? The only problem we have is this is a resonant 34. The first layer is 7 cross 7 cross stride 64. The resonant 34 is trained on 224 cross 224. First 7 cross 7 is going to reduce that to 112. Then my 3 cross 3 max filling stride 2 is going to reduce that to 56. This block is at 56. Then this block is at 28. I have a stride of 2 at the beginning of this block. This block is at 14. This block is at 7. And then we are doing a gap. Right? I am using what? CIFAR 100. CIFAR 100 is what? 32. 32 becomes? Right? Let's try it again. We are starting at 224. That becomes 112. That becomes 56. That becomes 28. That becomes 14. That becomes 7. Did I do something wrong? Yeah, I've written it one step ahead. Okay. The input to this is 224. The input to this is 112. The input to this is 56. The input to this is 28, 14 and 7. Now input to this is now in case of CIFAR 100 32, which means the input to this is going to be the second one. This basically is going to be 16. Then the input is this is going to be 8. This 2. How will you convolve now? You can't do that. If you do that, you're going to say train again. Or think about can you do it or not. This is clear? It's a very subtle question. Just think about it. Can you add padding and do it? If I can't add, you should be able to do first of all. Think why you should be able to do. No weights has to change if you're adding padding. Padding has nothing to do with the weights. Think about it. Second thing, if I'm getting done with my 4 or 2 here, should I stop there or not? But if I stop there, then what happens? I don't get these features. Then ask the question yourself, do you want these features? You don't want, so I don't want to answer, but think about it. It's clear? It's a very simple problem, just think about it. It's a thought-based question.
But they would have kept padding equals to same, right?
Sorry?
Padding equals to same they would have set in the model.
I already set. Then what?
Half, like the size won't get half.
No, every time you're using a stride of 2. Clear? Any question?
We can remove last two.
You can?
Remove the last two layers.
You can do anything you want. See, there's no target accuracy given, right? There's no target accuracy given. Your accuracy should be more than 1%. There are 100 classes.
But ideally it would be greater.
It should be in 90s.
CIFAR 100, right?
CIFAR 100.
Rohit, is there only one solution to this problem or there can be many?
Sorry?
Is there one solution to this problem or many solutions are there? Is there one solution to this problem?
Many solutions. Many solutions.
Many solutions.
Yeah, so state of art is 91.3 right now. So I am hoping that you should be 80 and up. You're using a state of art ImageNet model and then doing transfer learning. You should be 80 and up. The state of art is 90. Cool? Not cool?